Hello everyone, this is my first video to the Algebra 2 group coming from my basement at my house rather than coming from my classroom at school. It's possible I'll get back into school yet again to make more of these, but I'm trying to keep at least a few weeks out on my videos, and I'm running out of some room, so I had to start filming again here to make sure that I stay out far enough. Today we're going to start diving into Chapter 12. Chapter 12 is all about probability. If we continue to do this over distance learning, we're going to be jumping around just a little bit and covering lessons that, first of all, I think are the most important ones. But secondly, and more importantly, I'm going to be picking out the ones that I feel like you can do well from afar. So there's definitely going to be some picking and choosing of homework and things like that, because the lessons that we're diving into can have some elements that are really simple, and then they have some elements that can be a lot trickier. So I just want to make sure that everyone can be successful as we move through all of this chapter. So in lesson 12.1, we're going to be talking about the fundamental counting principle, which is probably one of the most important topics when it comes to probability. And it's one of the most important for a couple of reasons. First of all, it's very easy to write problems based on the fundamental counting principle, which means that very often on standardized tests like the ACT, the SAT, the ASVAB military entrance exam, and the MCAs, they like to lean heavily toward these fundamental counting principle problems because they are very easy to write. I could write about 1,000 fundamental counting principle problems in less than an hour probably, by just slightly manipulating different pieces, and I can think of hundreds of different examples that work directly to them. The key to the fundamental counting principle is talking about the possible ways that we can do a compound event. So if we have an event that has multiple pieces to it, how many ways can we do such an event? So I'm going to give you two examples, and then I'm going to dive into the one of the homework problems, and then we're going to talk about one other piece, and then I'm going to do two more fundamental counting principle examples, but I'm going to do them in a slightly different way. So my first example is getting dressed in the morning. So let's say that I have 3 pairs of clean pants, and I have 3 clean shirts and 2 clean ties. And I want to see how many different outfit combinations that I can make from these elements. So I have 3 clean pairs of pants. Let's say that they are blue and black and tan. So I have blue pants, I have black pants, and I have tan pants. And then I have 3 shirts. Well, let's say that the shirts are purple, blue, and green. So I'm going to come into my pants selections, and I'm going to say, well, if I'm wearing blue pants, I could wear my purple shirt. If I'm wearing blue pants, I could wear my blue shirt. And if I'm wearing blue pants, I could wear my green shirt. If I'm wearing my black pants, I could wear my purple shirt. If I'm wearing my black pants, I could wear my blue shirt. And if I'm wearing my black pants, I could wear my green shirt. Now I know some of you are saying some of these combinations may not look very well together, and that's true, but we're going to ignore that idea. Purple, blue, green. Then when we come off of that selection process, we're going to go into our ties. So let's say that I have a math tie and I have a sports tie. So off of each of my shirt pants combinations, I can have my math tie or my sports tie. Math tie, sports tie, 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 math tie, sports tie. This is what's known as a tree diagram of my situation. So it highlights the entire sample space. Sample space is all of the options. So if the book mentions sample space, that's all options that I have. And so if I go in here, I can find all of these different options. Maybe blue pants, green shirt, and math tie, or black pants, blue shirt, sports tie, or tan pants, purple shirt, math tie. These are all possible options that I have when I'm going to get dressed this morning. And if I just look at the last column of my tree diagram, I can figure out exactly how many different options I'll have because they all branch to this point. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18 different options of outfits that I can create from this combination of events. Alright, if you need another second to copy this down, go ahead and pause me at this point in time. But I'm going to move forward into another example now. The next example I'm going to talk about is food-based because Mr. P is always thinking about food. Even though I just ate lunch, I'm still thinking about food. So let's talk about dessert. How about ice cream? Let's say that I'm going to make an ice cream. So I have 3 different ice creams in my freezer. I have vanilla, strawberry, and chocolate ice cream hanging out in my freezer. Vanilla, strawberry, chocolate. And then also in my refrigerator, hopefully not in my freezer, I have some syrup. And no, not maple syrup, but chocolate syrup and strawberry syrup. So my vanilla ice cream could have chocolate syrup or strawberry syrup on it. And my strawberry ice cream could have chocolate syrup or strawberry syrup on it. And my chocolate ice cream could have chocolate syrup or strawberry syrup on it. And then let's say that I have some toppings. Let's say I have some candy sitting around the house because it's been Easter. I have some M&Ms. And I have some jelly beans, which would make a disgusting ice cream, but that's life. So M&Ms, jelly beans, 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 M&Ms, jelly beans. So now I have another tree diagram of my situation, and I have all my sample space hanging out here. I could have strawberry, strawberry M&Ms. I could have vanilla, strawberry, and jelly beans. I could have chocolate, chocolate, and M&Ms. That would be a chocolate on chocolate on chocolate dessert. So I, in total, have 2, 4, 6, 8, 10, 12 different options of how to make an ice cream. Now this has to be a simple situation. Okay, so some people are thinking, well, why not just put chocolate and strawberry syrup on it? That's a distinct possibility, but it adds an entirely new element to this situation, which we'll deal with as we move forward in lessons. All the situations we're dealing with right now have to be simple situations. We're only choosing one thing from each category, because if we have multiple things coming out of each category, that really changes the aspects that we're working with. All right, again, if you need it, pause me at this point in time. because I'm going to do a tree diagram example from our homework. For those of you who would like to follow along, the homework is on page 715. And I'm going to do problem number 13 with you, and then we will have completed this task. All right, so problem number 13 in your homework says we have a family that has 3 children, and we want to create a tree diagram of the boys and girls across the 3 children and figure out how many options there are. So child 1, child 2, child 3. So child 1 could either be a boy or a girl. And then from that, child 2 will either be a boy or a girl. And then from that, child number 3 will either be a boy or a girl. That was a bad B. So that gives us several options within our sample space. I could have boy, 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 girl, boy, girl, boy, boy, girl, 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 boy, boy, girl, boy, girl, 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 boy, or girl, girl, girl as my combinations. And every one is uniquely different. That gives us 2, 4, 6, 8 different options within our sample space. So this entire thing is the answer to problem number 13. We need to create our tree diagram and then count the number of options when we're done. Now remember, when you're counting options, only count the last column. And not all of them will have 3 columns like the ones I've been doing. Some may have 2 columns, some may have more than 3 columns, but always count the last column from your situation. All right. Now we'll go into the next topic of discussion, which is independence versus dependence. A situation is independent if our first choice does not affect the second choice. So things like, if I'm going to pick supper for tonight, I need 1 protein, 1 fruit, and 1 vegetable, and then maybe a starch for supper tonight. The protein I choose technically doesn't affect the fruit I choose or the vegetable I choose, because fruits are not also proteins, vegetables are not also proteins. Now there are other things that weigh into this. Yeah, I understand that certain things pair better with other things, and if I have chosen 1 protein, I may be leaning toward 1 type of vegetable. Like Mr. P always likes to have corn with spaghetti because they just pair well together. But just because I'm having spaghetti and meatballs as my protein starch combination does not mean that I have to choose corn. It just means that corn is my better option. Now, 2 events are dependent if the first choice, F-I-R-S-T, how about? If my first choice affects my second. Now this happens when the 2 things have overlapping groups or interconnected. So if I'm going to pick 2 proteins, let's say I'm planning a party and I want to have options for my proteins. Well, once I pick my first protein, I'm not going to re-pick it. If I'm picking proteins for a wedding, I'm not going to pick lobster and lobster. that doesn't make sense. Once I've picked lobster, then I have to pair another protein with it. I can't re-pick lobster. Just like if I go to the library and I'm going to check out some books, if I've already checked out one book in a certain type, I'm probably not going to check out a second book in that type, or I might, but it's going to affect the choices I have. So the first choice is affecting the second choice directly because they're connected. Now, this part of it can get a little hazy for some people, so hopefully it'll go fine. There's only a couple of questions in the book that talk about independence versus dependence, and the one I want to talk about is problem 18, which says selecting a fiction book and then selecting a nonfiction book from the library. So first of all, these two events are independent because there's no overlap between them. If I go to the fiction section and select a book, and then I go to the nonfiction section and select a book, the two books are not going to affect each other at all. Now, there may be some theming and things like that. Like I said before, where with my meal, my protein may pair better with something else. If I'm really into dinosaurs, I may pick a fiction and nonfiction book that are related to dinosaurs. But that doesn't mean that the two events weren't independent still. The way they would be dependent is if I'm picking from the same pool somehow. So if there are fiction books that are also nonfiction books, that would be a problem. But that is not the case. Now they have some like historic fiction and things like that, which are kind of a gray area, but there's still fiction books versus nonfiction books. So just ask yourself, is there overlap in this grouping? Does the first choice really affect the second choice? And if you're having questions on this or issues, these are really easy questions for Mr. P to answer over email. So just send me an email. So again, the answer to problem 18 is independent, and it's because we just talked about it. Okay, we just talked that out, that fiction and nonfiction books do not overlap. So now let's focus on the fundamental counting principle. I want to go back to the example that we had with the family. So we had boy, girl, and then boy, girl, and then boy, girl, boy, girl, boy, girl, boy, girl. So the fundamental counting principle is going to pull this one step further and say, you know what? Instead of looking at the tree diagram and the full sample space, which you have to do in the first ones, by the way, you can't skip the tree diagram. But instead of looking at the tree diagram and really looking at the full sample space to determine how many options I have, I can take the options I have at each layer and multiply them together to get the total number of options. Okay, so instead of looking at this as a to get my 2, 4, 6, 8 options here, I could say, well, when I have my first kid, there's 2 options. It's either going to be a boy or a girl. And when I have my second kid, there'll be 2 options. It'll either be a boy or a girl. And when I have my third kid, there'll be 2 options. It'll either be a boy or a girl. And despite what some people believe, there's no effect between the first kid and the second kid. These are independent events, which they have to be in order for the fundamental counting principle to work. If the events were dependent, this would be a whole different discussion. But if we take our 2 options for our first kid, our 2 options for our second kid, and our 2 options for our third kid, we get 8 total options. This is going to allow us to move forward into even more complex problems in the very end of the section here. So in the back part of this, we're going to have some problems on fundamental counting principle that really have us hone our skills on some more difficult situations, like problem number 22, which is next on my list. How many different batting orders does a baseball team of 9 players have if the pitcher has to bat last? So I have 9 batting positions. However, my pitcher is batting last, so he doesn't have a choice. He is the only guy sitting in the last position, and whoever I put in my pitcher position, he's batting last. So I have one option on who I want to bat last. It's the rest of the order that really makes the difference. Now, it doesn't matter where you start in your order. If I was creating a batting order, if I was really creating a batting order, I would be looking at the 3rd and 4th position. For those of you who deal a lot with baseball and softball, those are the 2 most important positions in your batting order. However, that first position can often be very, very important as well. You want to have your most consistent hitter in the first position, or your fastest guys in your first 2 positions, and then your most powerful hitters are usually in your 3rd and 4th position. But I'm not physically creating an actual batting order here, so it doesn't matter where I start in my order. When I start down here on the end, let's say that I'm starting with position number 1, how many different guys could I put in that position? Well, there's 9 guys on a baseball team at any given time, and the pitcher is already here. I can't put him down here. I have to put him here. So I have 8 guys that I can choose from when I go to pick my first batter. So any of those 8 players on my baseball team could end up in that first position. Now, once I've picked that position, this person, whoever they are, is there. So now when I move on to pick my second position player, I don't have 8 options anymore. I only have 7. And then when I go to pick the next position, I only have 6. And see, my choice gets easier as I go. Once I start putting people in places, I have less people to choose from, all the way down to the bottom. Now, if the pitcher did not have to bat last, if I could put the pitcher anywhere, the one major effect it would have on this situation is that I would have started with 9 players when I was putting my first position in place. Now, the reason it doesn't matter what order you pick your positions in is we multiply all the way down anyway. So if I had picked the 3rd position first and then the 4th position, I would just be switching around my 8, 7, 6, 5, 4, 3, 2, 1, 1. They would all be the same numbers. They would just be in a different order than they currently are. So then we can go ahead and go down the line and multiply through that to find out, in fact, how many players I ended up with. Now, for those of you who are seeing the pattern here, yes, this is a factorial. Sometimes these do come out as a factorial. This would be 8 factorial times 1, because this is the numbers 8 down to 1 multiplied together. So you could use a factorial to calculate it if you wanted to, or just multiply it out. So I have 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. We're going to see a lot of these factorial patterns in the upcoming problems throughout the rest of this chapter. So keep your eyes out for them. All right, the last one I'm going to do is problem 26, and then I'm going to leave you with your homework here. Problem 26 says, for a particular model truck, the dealership offers 5 versions of the truck in that model with 16 different colors and 8 different interior cab colors. How many possibilities are there for building a truck? So I have 5 different models of truck. I have 16 body colors, and I have 8 interior colors, or cab colors. So I have 5 times 16 times 8. Now this situation is more like my ice cream situation or my outfit situation from earlier, where I don't have a reoccurring pattern because I'm not pulling from the same pool. The difference between the two is this situation was a dependent situation. Once I placed one player, I had less players to choose from. Whereas this situation down here is an independent situation because the make of my truck does not affect the color of my truck or the color of the interior. Now, most of you would say the color of the exterior of your truck definitely affects the color of your interior, and I would agree with that. But in this instance, they want us to ignore the fact that there could be correlation here just in taste, though. There may be some yahoo out there who really wants a bright orange interior with a lime green exterior. It's certainly possible, but I would say he's a fool. All right, so hopefully we'll be able to get through this. This particular lesson shouldn't be too terrible, and hopefully this video wasn't too terribly long, because what we have coming is going to be a little more challenging as the chapter builds. Some of this probability stuff, like I said, stays very light, and some gets much harder. We're on page 715, working problems 12 through 27 today. And this should be coupled with our test for chapter 11, which hopefully went fairly smoothly for everyone. And then we'll be moving forward as we go on. It looks very likely, if we continue distance learning throughout the rest of the year, that chapter 12 will be the last chapter that we touch in, which is normal. Chapter 12 is normally the last full chapter we accomplish. We usually get a little bit, halfway or so into chapter 13. This time of year is usually really choppy, and we lose a lot of days anyway, so we're really not losing a whole ton of education here with our distance learning, timeline-wise. Anyway, have a great week.